that's a lot of past, not a lot of current in there. So I'm just a has-been. Oh yeah, no, that's not a problem. Yeah, it's a lot. Might sound as if I'm a has-been more than anything, and that might be true. So again, my name is Jeppe Kjaersgaard. I'm here today formally as an adjunct professor from South Dakota State University, but I am working at the Minnesota Department of Agriculture also. And I just want to provide a brief update on a project that we've been working on for a little bit of time now, and that is to estimate the crop water needs from subirrigation in the northwest Minnesota. And it's really a companion study to one that Chris Hay and Matt Helmers presented on at the Drainage Research Forum in Ames, Iowa in November last year. And so just a brief outline of this presentation. So we'll show some data of our estimations of the crop water use and following yield, and then compare those estimates. They are all model estimates, and compare those to a field site that we've been working on now for a couple of years. So the overarching objective here is to estimate the water limited yield gap. I think Chris showed this figure yesterday as well. And so that is to try and get at closing the yield gap. So where we have an actual yield out on our right that is lower, and in some cases considerably lower than the yield potential. Of course, there are a lot of reasons for that, but there are a lot of limiting factors, but one of them certainly is water. And so what we're trying to get at here is to tease out, well, how much of that yield differential is due to water, and can we close that gap by supplying additional water to the crop. And so in the absence of a long-term data set, we went the modeling route. We're using the hybrid maize model that was developed at the University of Nebraska-Lincoln. And one of the reasons was we heard Jeff just talk about how harsh the conditions are up in Minnesota. And so here is just the title of I think it's might be the most recent paper from the team behind hybrid maize. And you'll notice the title there that they state it is for use in harsh rain-fed environments. So we thought that was very appropriate for this study. But the model is, joking aside, the model is developed primarily for Midwestern growing conditions. So that should be pretty appropriate for this study. So we selected 4 studies in northwest Minnesota in the Red River Basin, ranging from Stephen in the north, which is about a couple of hours south of the Canadian border, and then down to the southern part of the valley. All the sites are fairly close to the Red River, 3 of them in Minnesota and the 4th in North Dakota. Another snapshot there just showing where those field sites were in the scheme of the outline of the Red River Basin. That is what is kind of in that lighter brown color in this figure right here. And so for transparency, I guess, and for consistency with other project presentations, here are some of the inputs that we used for this modeling. We ran it for a total of 15 years, and well, some of the input parameters we used here is shown in this outline here. So the corn varieties we used are typically in that 92, 95, 97 day corn. We ran the study both for rain-fed conditions, so the actual climate, and then another scenario where we were able to, on the conditions where we were able to irrigate the crop, so we were not under water-limited condition. And so if that was the case, we assumed that we probably would increase our population rates a little bit, and so the population rates are a little different between rain-fed and irrigated conditions. And then the max rooting depth, it depends a little bit on the site, or depends on the soil type that we used at our various sites. All the weather data came from the North Dakota Ag Weather Network, and they have weather stations close to these different locations. And then most of the soil types up and down the valley there are clay loams or silty clay loams, with one exception. There's that Stephen site that's a little further to the north in that area. They have some very fine sandy loams. So that was what we used for this study. Jumping straight into the results, what we did find was that irrigation was needed most of the years. They varied a little bit from site to site. In this case, the sites are listed from south to north. So Tinta on the left, that is the southernmost location, and then Stephen is the northernmost location. It would have been nice if there was a north-south gradient in the data, and if we skip Eldred, that might be the case, but certainly we saw that most years that the crop would benefit from additional water, that it was running short there during the growing season. Oh yeah, and I misspelled Eldred as well, so just to point that out. And so just summing up the data from all sites at all years, it looks like this, and it's just really difficult. So the years along the bottom there, and then the depth of irrigation that is estimated by hybrid maize that is needed is shown here for the different sites. And there's a lot of information, and it's not really easy to kind of get a good overview of what that looks like. But then Chris had a great figure where he kind of graphed up this way, kind of with dots, I guess, that kind of shows it in a little bit of a different way. So I thought I would copy that. That was a great idea, so I copied that for my presentation as well. Yeah, yeah. And so again, the depth of irrigation there on the y-axis, and then location along the bottom. And if nothing else, kind of the relative shape of the cloud of bubbles there shows where that certainly in the southern part of the valley, again, there's the Tinta over on the west, that we have more years where a greater depth of irrigation would be beneficial, as compared to Stephen, our northern site, that even though we have a few years where the absolute amount is higher than the other sites, but there are fewer years where a higher level of irrigation would be beneficial. And so I think we would expect that is what it would look like. But we certainly see that in many years we are in that 3 or 4, maybe even 5-inch range of supplemental irrigation to fully meet the crop water needs. So just jumping forward as well, and looking at, well, what were the yield differences between rain-fed conditions to a condition where we were not short of water or in an irrigated condition. And so that was getting that yield, water yield gap. So that is what is shown. So the average yield for each product site across all 15 years is what is shown here. Blue lines are the rain-fed, and the orange bars, I guess, are the irrigated ones. So certainly there's a gradient across the valley, higher in the south, slightly lower in the north, as would it be expected. But what was maybe a little surprising to me was that water yield gap was fairly consistent across all sites, in that 35, 38 bushel range. So even though the absolute yields were decreased as we were heading north, the water yield gap was fairly constant across all sites. But again, this was all estimated from the hybrid maize model. And so we have now for a couple of years been working with our producer in the valley by Tinta, so that's the southernmost site, who installed a sub-irrigation system on his farm a couple of years ago, just before in 2015, excuse me. And so we've been working with him a little bit, but we're just collecting some information from his field site. He did all the design, all the installation, so that it fit to his production. So it's 221 acres in size, so it's a fairly sizable chunk of land, and it's a full mile long, and there's about not less than 8 inches of elevation difference from one part of the field to the other. So it's flat, and there's next to no grade up in this area. So the way he irrigates is that he has a well. He irrigates from it, located up in this, it was an abandoned irrigation well that he has now repurposed for the sub-irrigation piece, and then he is pumping water back into his drainage control structures there along the northern end here, and then he keeps pumping until the water reaches within a foot of the ground surface all the way at the other end, and then he kind of maintains that level while he irrigates. So fairly straightforward way he's running it. To my knowledge, he's not running any irrigation schedule up. He's just having a pitchfork and dig a hole and take a look at the soil and by feel figure out how much irrigation is needed. So in 2016, this field was planted to corn, and hybrid maize for 2016 estimated that almost 2 inches or 1.9 inches of irrigation water was required to fully meet the crop water needs. The producer here applied about half of that, about 0.9 inches of water. The yields were somewhat different between what we estimated with hybrid maize and the observed values. So on the left are the rain-fed and irrigated yields, again for corn there in 2016, where we had about a 30 bushel difference, so a 30 bushel yield gain with the model values, whereas the observed numbers, and say for the observed, the irrigated is from the field I just talked about, the non-irrigated is from a field just across the road that the same farmer manages as well, and was managed the same way. So that's the observed values. And there was only a little, about 5.5 bushel yield increase from the irrigation. So certainly a much smaller benefit from that supplemental irrigation than what was modeled. And in addition to that, the absolute yields were quite a bit higher in the observed than they were in what was modeled. And so we're looking at that now as to why that is, and that certainly has to do with both the timing of that rainfall, and then also, as was discussed yesterday, Tom, with some of the just the amount of soil moisture that is available, not least through capillary rise, that might not be fully accounted for in that model. And then just based on that 1 year, again, it was in corn in 2016, then it was in soybeans in 17, so I didn't bring that data, and then it's going back to corn for 2018, so we'll have another year to compare to. But we had that about a 5.6 bushel yield increase from the irrigation. And now I'm not certainly by no stretch an economist, and so I shouldn't venture into making any economic analysis, but just based on what the information that is known is that assuming a $3 corn, well then the gross increase or gross dollar amount on the yield increase is about not quite $17 an acre, but then if we pull out the cost of water, in this case is about $5 an acre inch per acre, that we'll subtract that means that we're down to about a little over $12 an acre. But then that does not, we still haven't paid for installation of the control structures and extra tile and so forth, and we haven't paid for the extra trucks that has to drive from the field to haul all the grain back to the farm and all that. So that will need to be factored in also, of course. And for the field as a whole, it's about $2,700 that grows, or that netted because of this. But again, all the expenses hasn't been factored in there. So with that, just briefly summary. So based on this data, again from the modeling there, that we did find that supplemental water would be beneficial in between 9 and to 14 years out of the total 15 years where we did the modeling, and that water yield gap was in that 35 to 38 bushel an acre range. But then at the same time, those modeled estimates, they did not match particularly well with the observed values, but it's certainly something we'll continue to watch. So that's what I had, Gary. I don't know if there are any questions. Oh, Tom, sorry.